Hello everyone, I'm Yao Li from Chang'an University. In this lecture, we are going to learn some basic knowledge about lateral earth pressure at rest. In geotechnical engineering, it is often necessary to prevent lateral soil movement. Any movement of soils may cause severe damage to surrounding buildings and infrastructures. Those figures show some of the methods used in engineering to prevent the lateral movement of soils, including retaining wall, braced excavation, and anchored sheet pile. The first figure shows a typical retaining wall that is usually used in highway projects located in mountain areas. It prevents the lateral movement of the soils and protects the highway. The second figure shows a braced excavation in urban area. As we can see, complex structures are used to prevent the lateral movement of the ground. Braced excavation is widely used in foundation pit excavation and subway station excavation, where there is a complex stress conditioning and the huge lateral stress caused by the surrounding building and infrastructures. Those figures show failure of some projects where large lateral stresses were developed and supporting structures were failed. Those failures will endanger the constructed project, surrounding building, and infrastructures. This is why we need to learn how to calculate the lateral earth pressure so we can build a safe supporting structure. So how to design an earth retaining structure? To be able to design them, we have to estimate the lateral earth pressure acting on those structures. In order to calculate the pressure exerted at any point on the wall, the following must be taken into account: natural and the type of the soil, type of the wall, materials used in the construction of the wall, height of the water table, subsoil water movements. For retaining structures such as the figure shown, we need to consider two factors in design, which are earth pressure sigma, it is the earth force in unit area. Earth force E is the earth force acting on the unit length, as indicated in the figure. Now let's have a look at the lateral earth pressure at rest. It applies only if the wall doesn't move. In the figure, the wall moves towards the left. As a result, the left part of soil is pushed by the wall. The pressure is called passive earth pressure. The right part of soil pushes the wall. The pressure is called active earth pressure. Those three lateral earth pressures are used to calculate the acting lateral earth pressure in corresponding cases. Lateral earth pressure at rest can be calculated in homogeneous natural soil deposits, where the ratio of the effective horizontal stress divided by effective vertical stress is a constant. The constant is known as the coefficient of earth pressure at rest K0. It should be noted that the relation holds true in effective stresses, not total stresses. K0 state is also called geostatic state, in which there are no lateral strains. For normally consolidated soils and granular soils, we can use the first equation to determine the K value. For over-consolidated soils, we can use the second equation to determine the K value. As we can see, the two equations are related to friction angle. For elastic analysis, the third equation can be used. This figure shows the calculation of lateral earth pressure at rest, where backfill contains one kind of soil, so the effective horizontal stress equals K0 multiply sigma V prime, where the sigma V prime equals height of the soil multiply unit weight prime. As we can see in the figure, the effective horizontal stress increases linearly from the top to the bottom. When the backfill contains multiple layers of soils, the second equation can be used to calculate its effective horizontal stress. For soil above water table, we can easily calculate the total force per unit weight, E, using the equation as we can see in the equation. E equals the area of the triangle we draw in the figure. The acting point of the E is 1/3 of H. According to the geometry of a triangle, it should be noted the E we calculated is a force which must have the acting point. This figure shows the calculation of the lateral earth pressure at rest where soil is partially submerged by water. As we can see, the water table is H1 below the surface. So we need to divide the soil into two layers, one above water table and one below water table. Since different unit weights will be used in the calculation. For soil above water table, effective horizontal stress equals K0 multiplies sigma V prime, where the sigma V prime equals gamma multiplied H1. For soil below water table, effective horizontal stress is divided into two parts, pressure caused by soil and pressure caused by water. Pressure caused by soil equals K0 multiplied effective sigma V, where the sigma V prime equals gamma prime multiplied H2. Gamma prime equals saturated unit weight minus water unit weight. Pressure caused by the water equals K0 multiplied sigma V prime, where the sigma V prime equals gamma W multiplied H2. Before active condition occurs, there is no lateral movement of the wall, and soil is under K0 condition. As the wall moves away from the soil, active condition may occur. The effective vertical stress remains constant while the effective horizontal stress increases till reaching the failure envelope. Then the soil fails. This figure shows the change of the stress state from the initial K0 state to failure state while the effective horizontal stress increases. During active condition, the wall moves away from soils. As a result, part of the soil mainly near the wall are stretched since the boundary is moved away. Then, a shear failure plane is formed in the soil, as shown in the figure on the right. The failure plane is 45 degrees plus half of the friction angle to horizontal, as shown in the left figure. It should be noted, active condition occurs only when certain wall movement is reached. This table shows the horizontal movement required to reach the active condition for different types of soils. As we can see, the movement is related to the height of the wall H. Before passive condition occurs, there is no lateral movement of the wall, and soil is under K0 condition. As the wall moves towards the soil, passive condition may occur. The effective vertical stress remains constant while the effective horizontal stress increases till reaching the failure envelope. Then the soil fails. This figure shows the change of stress state from the initial K0 state to failure state while the effective horizontal increases. During passive condition, the wall moves towards soils. As a result, part of soil mainly near the wall are compressed since the boundary is closer. Then, a shear failure plane is formed in the soil, as shown in the figure on the right. The failure plane is 45 degrees minus half of the friction angle to horizontal, as shown in the left figure. It should be noted, passive condition occurs only when certain wall movement is reached. This table shows the horizontal movement required to reach the passive condition for different types of soils. As we can see, the movement is related to the height of the wall H. Now we have some basic knowledge about active soil pressure and passive soil pressure. To calculate the pressure, we need corresponding factors, K active and K passive. We will learn how to get those factors according to Coulomb's theory and Rankine's theory in next lecture. Here are all the contents in this lecture. Thanks for your listening and see you next time.